I just hope that it's not because. Okay, nice. I just don't know how to put it. I just put it into my pocket. Okay. So this is. I think those of you who have already has been at my one of my previous talks might know what is the question I am going to talk about, but I think it is still worth beginning with the beginning and giving the introductory part as if nobody is in the know of the field beyond this. So suppose we have a manifold M with a bivector field pi. So pi is a section of the exterior square of tangent bundle of M. And pi verifies the following condition. I actually don't care much about this condition, so I'll just probably put it like this. We have for every two, so to take Poisson bracket of f and g given by the formula, by vector fields, you can always couple with a pair of covector fields. So when you have two functions, you take the derivatives, take the differentials, and then you pair the bivector field with the differentials, you get a function again. So you define the Poisson bracket of f and g by this formula. And then the assumption, the condition we assume is that this bracket verifies Jacobi identity. Equivalently, one can formulate this condition in the terms of so-called Schouten-Nyquist brackets, and this gives you the following type of equation. So the square brackets here are Schouten-Nyquist brackets on bivectors, and we have to put this bracket of pi with itself equal to 0. These brackets are graded skew commutative, graded skew symmetrical, and therefore the bracket of pi with itself needs not be 0 identically, because pi has degree 2, and so when you take this bracket, it's rather an anti-bracket here than the usual bracket, but it's traditional way of writing down this condition. So we have this Poisson structure in manifold, and when we have this, one can look for so-called integrable systems or large commutative families of functions on M, commutative with respect to the Poisson bracket. So we are looking for collections for algebras A inside of C infinity of M, such that for every two F and G in A, the Poisson bracket F and G is 0. One such algebra is universally known as the so-called center of the Poisson structure, or the space of Casimir functions, that is the space of all F in C infinity of M, such that for every G in C infinity of M, the Poisson bracket of F and G vanishes. This center needs not exist. And if, for instance, the Poisson bivector is non-degenerate, then there are no non-trivial Casimir functions except of the constants. But still, in many important situations, the Casimir functions or the center of the algebra are large. For instance, the main example for us today will be M equal to the space of the coadjoint representation of a Lie algebra. The Poisson bivector, if you write it down explicitly in terms of coordinates, is given by the following formula. It's it is it is something like Cij k x k, where x1, xn are the coordinates in G star, and the same, identically, they are just elements in the basis of G, and C, I, J, K are the structure constants. That is to say, the commutator of Xi and Xj in the Lie, in the sense of the algebra, is equal to C, I, J, K, Xk, just this. So we have this canonical example, and in this case, the center of the Poisson algebra, C infinity of M, well, we usually substitute it by just the algebra of polynomial functions. So we replace it with S of G, which are regarded as polynomial functions on G star. The center is pretty large. The center here, for instance, the center, Poisson center in this case, consists of all functions in SG such that f of GX G minus first equal to f of x for all G in the Lie group associated with the Lie algebra. Of course, I'm taking only connected Lie groups. So it goes without saying that there are only connected Lie groups for us. So this center is pretty large. And in this case, this construction is non-trivial, of course. We go on. Of course, so the center is something standard, but one, of course, needs to find something not so rare, not so evident, to be able to talk about some non-trivial geometry on the Poisson manifold. And this non-trivial, and so there are many examples of non-trivial commutative Poisson subalgebras in this case, but I'm going to talk about one particular construction which goes as follows. Let psi be a vector field on M. We assume that psi verifies just one condition. The Lie derivative with respect to psi of pi, well, it needs not be zero. It is just pi sub psi, but the Lie derivative of this by vector pi sub psi should be zero. So the square of the Lie derivative kills the Poisson vector. In this case, it is a matter of, well, it's a kind of easy exercise for, well, for the first year students to prove that for every f and g in the Poisson center of C infinity of M, therefore we were looking for the Poisson center, therefore we needed this Poisson center. It is for this reason. For any two f and g in the Poisson center, and for every natural numbers p and q, and maybe zeros, but that's not interesting, the Poisson bracket of the iterated different derivatives of f with respect to psi and of g with respect to psi vanish. So these functions are no more in the center unless phi sub psi is already 0. And therefore, this gives us a pretty large non-commutative commutative subalgebra in the Poisson algebra.
They are not in the center itself.
Yeah, but they commute with each other. They are large. Actually, in many cases, for instance, I'm going to talk about this situation. This subalgebra is known to be maximal. And moreover, this construction is closely related to the so-called Leonard-Magritte induction, another method to obtain large commutative subalgebras. Also quite mysterious, I'd say. It works, but why it does? Well, in Leonard-Magritte induction, you need to have two compatible bivectors, Poisson bivectors, and here they are, number 1 and number 2. They're degenerate. They're compatible, yeah. Yeah, compatible, and they're both Poisson. Right. So here's the example we were looking for is the following. You take M again equal to the space of coadjoint representation. We take psi to be equal to any constant vector field, psi alpha times d over dx alpha. Psi alpha just constants. Real or complex, it doesn't actually matter which number field you choose. Then these conditions hold automatically, because if you look here, coefficients of this bivector, they are linear, and psi is constant. So when you differentiate twice linear functions with respect to a constant vector field, you get just 0. So everything holds, but it is known in many situations that what we obtain is actually maximal commutative subalgebra in the Poisson algebra. So this is a very powerful method in spite of it being pretty simple. And when I say it is simple, I really mean it, because just a remark, I think it is worth making this remark here. Remark is as follows. This condition, this geometric condition, it can be rewritten in pure algebraic form as follows. Take so Poisson bracket with the index psi will denote the Poisson bracket with respect to the bivector pi sub psi. Right? It is easy to see that it is equal just to the following combination. You take the derivation of the Poisson bracket of f and g with respect to psi and subtract all other possible places where I can put psi here, right? Here and here. Right? Now the condition that L psi of pi psi vanishes, well, it is it can be rewritten in the following way. You take the same formula, but you substitute brackets with psi, with index psi instead of usual brackets here. Then you should get 0 on the left. So this is a pure algebraic condition. We actually don't care about linearity of psi. We don't care about the bracket being Poisson bracket, being anti-commutative, verifying Jacobi identity. Nothing actually matters. The only condition is that this formula being applied twice vanishes. So if you iterate this procedure, pure algebraic procedure, you get 0. And in this case, it is also possible to prove by the same inductive reasoning I mentioned that the same conclusion will hold. So the nature of these brackets, the nature of psi, are totally not important, are totally arbitrary. So one can ask whether one can find other examples of brackets, other examples of operators psi that will give you this type of relation. And my talk will be about an attempt to obtain, if not this type of relations, and at least to obtain some kind of operator that would verify, that would give you large commutative family of elements in non-commutative algebra. So, I mean, in the ultimate purpose, the ultimate goal you can pursue is to find the construction which would allow you to transfer this mechanism of constructing commutative subalgebras from Poisson algebras to their quantization, deformation quantization, or geometric quantization, whatever you can think of, right? However, for me, well, the only thing I'm going to talk about will be this particular example where the Poisson manifold is given by the space of a dual representation, a dual adjoint representation. And the vector field is given by this formula. So I'm going to talk, from now on, I'm going to talk only about this particular case. And in that case, the quantization of the symmetric algebra of G is well known. So I have S of G, and then you pass, and then, well, you can use whatever quantization procedure you can think of. You can use either Kovacevic quantization, or so-called Poincare-Verhofstadt quantization, or any other construction that they exist. Well, in any case, whatever you obtain will be equal to the universal enveloping algebra of G. And now the question is, suppose you have, so we have this commutative subalgebra, which I'm denoting by A sub psi. The question, if there exists A hat sub psi here, which corresponds to A sub psi under the following construction. You take, so you probably all know that universal enveloping algebra of G is filtered. Such that the associated graded algebra of this filtration is equal to the symmetric algebra of G. That's the Poincare-Verhofstadt theorem, actually, right? And one can now ask that the image of A hat sub psi under this factorization will be A sub psi. Значит, Xi — это просто векторное поле на... Да. Да. Значит, A sub psi, A Xi, Xi — это коммутативная алгебра, полученная вот такими методами. Да. Это просто берем всевозможные производные элементов центра. Вот. И мы хотим теперь описать. Значит, вопрос состоит в том, как получить вот такую алгебру в универсальном обертывающем. Вот. И, как я понимаю, общего метода для всех универсальных обертывающих неизвестно. Для полупростых есть метод, который придумал Леня Рыбников. Okay, I'm going to talk about this in a moment. So, yeah. The algebra A hat sub psi is commonly known under the name of Mishenko-Fomenko algebra. That's due to the fact that the original argument shift construction, of which I had just erased in the blackboard, was first observed. Well, the general case of this construction was first suggested by Mishenko and Fomenko in 1978, I mean, according to Novikov's school, they did this because they picked it up from a paper by Monakov, but then they generalized it from
Why did they do?
Monakov did this for rotation algebras, for algebras of this orthogonal group, orthogonal algebras. He was working with solid body equations, and he observed this phenomenon there. And Mishink and Fomenko, they picked this observation up, and they proved that in general situation for any of the algebra, this will work. And ever since that time, well, there is a split between Novikov school and many people outside of Novikov school. At least, I know that at least Alexander Molev calls these algebras Mishink and Fomenko algebra. And yeah, and of course, people in my department call this algebras Mishink and Fomenko algebras as well. Yeah, it's kind of a little bit. It's a little bit of politics here. Okay, let's go on. So, equation. Find a hat sub psi inside universal enveloping algebra of G. The answers are known in many situations, but these answers are not satisfactory, and I explain why in a couple of minutes. So the answers are known, first of all, in case of G equal to GLN. It was the first case. It was observed by Tarasov, Alexander Tarasov, not the Tarasov which is now well known, but there was another Tarasov, a student of Wimberg, who in 2001, in a paper published in 2001, I think, proved the following fact, theorem. Take the following generators of the center of UGLN. So you have the center of UGLN, and its center is well known. It is known that it is always a free algebra, free polynomial algebra in n generators, with n generators. There are different choices of generators one can suggest. So the most popular one is the following. Take the characteristic polynomial of a generic matrix L, generic matrix, n by n matrix, with commutative entries. So when you want to write down its characteristic polynomial, you subtract identity and take determinant. So then you decompose it as polynomial over lambda, and the coefficients of the polynomial, they are polynomials of L, of the entries of L, and they are called the coefficients of the characteristic polynomial, and they are known to generate the center, the Poisson center of GLN, right? Yeah, that's another choice, and that choice, yeah, that's another choice. The traces of powers of L, that's another choice of generators, and it seems to be much more complicated than this one. This one is much more popular, and this works much better, and as far as the construction we are going to talk about, than the traces of the powers of L. Somehow, I don't know why. Of course, there are different. There are lots of different choices that are all equivalent. There is nothing different. You can just change. You can always express one of the elements in terms of the other. So z sub z sub pi of s of G Ln is known to be the algebra of this coefficients, right? Then there is canonical map, which is used in von Graeber-Hopf theorem, symmetrization map from SGLN, actually from SG, for any of the algebra, to universal enveloping algebra of GLN. It is given by the following formula on monomials. If you have a monomial x1, xn, so xi, probably I1, in beta, im, I, they are generators of GLN. So we have a monomial. And its image will be equal to 1 over n factorial, sum of all permutations S of the group Sn, x, I, S of 1, x, I, S of m. Sorry, m factorial, of course. So these x's on the left, they're generators of SGLN, so they commute. Meanwhile, these x's on the right, they're generators of universal enveloping algebra, so they do not commute, right? But I don't use, I use the same symbols for them. Sorry for this. So there is this map, and we consider the following. Now Tarasov proved the following fact. Yeah. This is sometimes called von Graeber-Hopf quantization. So here's the theorem by Tarasov. Take psi equal to any constant vector field. Vector field on differentiation on GLN. Right? So you have this differentiation. Take psi p applied to ik of L and symmetrize this. Then for all p and k and q and L, these elements will commute. Yeah. So if you just symmetrize the generators, so the elements in parentheses, the elements to which we apply sigma, they're actually generators of the commutative, of the Poisson commutative Mishenko-Fomenko algebra, or argument shift algebra. They're generators, actually. So what Tarasov proved was a very naive thing. If you take generators of this form, you cannot do this with other form of generators. But if you take generators of this form, symmetrize them, then you will get a commutative family of elements in the universal enveloping algebra. So in this way, you obtain a large commutative subalgebra in UGLN. But remark, you don't have a shift mechanism. You just do this in terms of the generators. You cannot, there is no map from UGLN to UGLN which would play the role of a shift in this non-commutative setting. You just have the algebra. Well, a bit later, like 2006 or 2007, there appeared more general construction by Rybnikov, Lenya Rybnikov, who suggested another way to construct generators, again, generators of the argument shift algebra in UG. But this time, this construction was much more complicated. What Lenya suggested, he actually Well, let me put it in a short way. Arbitrary, semi-simple. G should be semi-simple. Arbitrary semi-simple. That's so it was a little bit more general than Tarasov's construction, but it still was not most general because the original construction of Mishkin and Fomenko, the original argument shift method works. This works only for GLN. Argument shift method on Poisson algebras on Poisson level works for any Lie algebra. And Rybnikov construction works for semi-simple Lie algebra. And what he did was he actually found a map from Kac-Moody algebra of G at critical level to UG. And then in Kac-Moody algebra on critical level, one knows that there is a large center composed of Sugawara operators, a so-called Frege-Frankel center. And then the image of the center will be the algebra A subset, A sub phi hat. The image of this of a Frege-Frankel center. That's not an easy thing actually, because in the original paper of Rybnikov, he couldn't even suggest explicit formulas for the generators of the center, because the generators of Frege-Frankel center are not known in explicit form except for some very particular cases. And it was the generators were later found explicitly by Molev and Yakimov and other people in this team, so to say. But still, you have the algebra, but you only can construct it in terms of generators. Moreover, it is remarkable that the generators that Lonya obtained in this way were some deformations of these generators. Again, so you cannot obtain generators of other types somehow. It's remarkable. So, so now what I'm going to talk about today, I am going to suggest an operator, a shifting operator, psi hat, an operator on UGLN, from UGLN to UGLN, such that this operator will somehow generate the argument shift algebra in the following sense. You take symmetrized images of the generators of the center. So you just take the symmetrized images of what they call the coefficients of the characteristic polynomial. Then you apply psi hat p times to these symmetrized images, and they will commute. So I somehow managed to pull this psi from under sigma. One, of course, can do this formally in Tarasov's case as well. I'll explain this in a moment. So in Tarasov's case, you can also try to pull this element, this psi, from under sigma using the Poincare-Verhofstadt theorem. You know, sigma is invertible as linear map. So they exist sigma minus first. You can do the following trick. You take U, GLN, then you take sigma minus first, you end up in SGLN, right? Then you apply usual vector field psi, and we go further in this formula, and then you apply sigma back, and you get an UGLN. So let's denote this psi double hat. So this psi double hat, well, it is a well-defined map, of course, but the problem is that you cannot write it down in some finite form. If you try to write down psi double hat on any element F in universal enveloping algebra, there is no way you can compute it unless you do all these tricks in both directions. So, I mean, of course, this psi double hat is very similar to psi, but it doesn't verify the Leibniz rule. I'm going to tell this in a couple of minutes. So let me first introduce psi hat. To this end, I need to describe the quasi-derivations of Pyatov, Saponov, and Gurevich. Originally, quasi-derivations appeared in the work of Pyatov, Saponov, and Gurevich as certain as limits of certain operators on the algebra they studied. They studied the so-called reflection equation algebras, and they show that when this reflection equation algebra is degenerates the universal enveloping algebra of GLN, then the operators that they introduced degenerate to certain operators on UGLN with very peculiar properties. So there are different ways to introduce these operators. I begin with the axiomatic way, and it is pretty simple because it's simple to do this. So for me, quasi-derivations are the operators given by the following three axioms. First of all, we set the generators of GLN, denote the generators of GLN by EIJ. So this EIJ, they're abstract matrix units. They're abstract matrix units. Right. So we set EIJ, the set of generators. And for future references, I'll denote by L the matrix of EIJs as an element in the n by n matrix space with coefficients in UGLN. Because, of course, GLN is a subspace in UGLN, as one knows. And the first condition we have, the first axiom is the following. Definition. Oh, probably it's better to say that it's not definition, it's what Grothendieck used to call definition/theorem, because I am defining an object, and at the same time, I have to prove the existence of the object which verifies these conditions. So definition/theorem. They exist. A unique set of operators Dij hat from UGLN to UGLN, which verify the following three axioms. First, Dij hat at 1 applied to the scalars vanishes. 2, what's wrong? Oh, someone is linking something. Someone is teaching something. I don't know. Sorry. Okay, the second axiom is the following. D hat ij applied to E PQ is given by delta, well, Kronecker deltas. IQ delta JP. So these axioms are evident, and of course they're verified by D double hat IJs, right? So if you take the partial derivative here instead of the general vector field psi, of course you get these two axioms. However, the third axiom is the most important one, and this is what makes the quasi-derivatives special compared to the construction on the right part of the board, the right side of the board. The third axiom goes as follows. For every elements f and g in UGLN, the operator Dij applied to their product of G is given by the following sum. So first of all, we have terms which come from the Leibniz rule. But then we have a third term, which looks like this. It is plus d j k, so the sum of k from 1 to n, d hat jk of f, d hat ki of g. So we have this formula. The difference between quasi-derivatives of Saponov, Pyatov, and Gurevich and that naive construction which we have here is that if you take d double hat ij given by this construction, then you will not get such a concise Leibniz variant of Leibniz rule on the right. In fact, you'll get an infinite sum of terms, infinite sum of operators of this type of double hat instead of this finite sum here. You'll only have an infinite sum of operators. It will never not ending. So the I would say that the Leibniz rule is not given by some finite formula in this case. It is given by some infinite sum of operators. And so far as I know, this is the only finite formula in this situation that one can find. So first of all, one can show that these operators are in fact well defined. And well, I can do this, but I think it is not worth the while because the proof is pretty evident. I mean, first to check that you can define Dij hat as an operator from the tensor algebra of GLN, the tensor algebra of GLN. And to this end, I just need to check that this formula is co-associative. So you just, I mean that if you have a triple product f, g, h, there are two ways you can expand the value of the operator d hat ij on this triple product, and you need to check that both constructions will give you the same formula, and that's easy to do. And the second thing you need to check it is that if you apply Dij hat to the ideal that determines, so ideal, I don't know how to put this way, ideal, it determines the universal enveloping algebra. And this ideal is actually mapped into itself by Dij. And to this end, it is check that Dij hat applied to the formula EPQ ERS minus ERS EPQ minus delta PS EQR plus delta UR EPS vanishes. And that's easy. You just do this by hand and get the result. So these operators are well defined. This formula is actually very concise and very it has a nice closed form. And for any element f in UGLN, we can actually find the value of dij of f in a finite number of steps. You just do this exercise, you just expand f as a product of two functions, two elements, then you expand these elements further, and after a finite number of steps, you get a finite formula for this operator. All right. And the conjecture, which I'm going to talk about, is that if you take psi hat given by the following formula, you take the sum over I and j from 1 to n psi ij d hat ij, where psi ij are certain coefficients, just some numbers, real or complex doesn't matter. Then psi hat to the power p applied to any element in the center will commute with psi hat to the power q applied to any other element of the center of the universal invariant algebra UGLN. And there are plenty of evidence that this conjecture should be proved. Plenty of evidence. So today I'm going to prove, for instance, that if you take f and g to be equal to, so if f and g are equal to the symmetrizations of the generators of the center, the coefficients of the characteristic polynomial, right? Then this will hold for all p and q. So that's one evidence. Another evidence is that no, this holds. This holds. Other evidence is the computations done by my PhD student Yasushi Ikeda, who proved two facts. For instance, here's what he proves: if you take f and g arbitrary in this elements in the center of the universal invariant algebra, and take just one derivation of f and one derivation of g, that this will commute. The other thing he proved is that you take arbitrary f in the center, but as far as g is concerned, you take g equal to trace of the power of the matrix of generators for any k. And if you take one derivation of f and two derivations of g, this will commute. And this is very non-trivial, actually, because if you try to write down a concise formula, well, a short formula for, well, you can actually find a short formula for the first derivative here, and that's how we can prove this fact. But if you try to do this for the second derivative, the formula starts to grow exponentially. There are lots of combinatorial difficulties you need to go through to overcome. And you also observe that you cannot derive, oh, sorry, I forgot to say where. So psi, yeah, to the power 2. I forgot, I said it, but I didn't write it. you take first derivative of f and second derivative of g. Second derivative. You see, the second derivative is much more complicated. It's exponentially more complicated than the first derivative. So proving this is quite a feat. And you cannot actually derive this from this fact. And that's because the Leibniz rule has this extra term in there. So you cannot just derive the properties of the combinations of the products of elements from the properties of the elements themselves, unfortunately.
Now this was invented by Georgy
Georgy Sharygin and Safon. Yeah. So I'm going to prove this fact now. At least I'm going to explain how this can be proved. But before this, I need to, I'll probably make a reference to my previous talk, which was in December. At my previous talk, I spoke about the first integrals of the Potter system, right? And I showed that certain elements given by the operators dk, there was the operators d sub k, and if you apply them to the same coefficients of the characteristic polynomial, right? And these elements will form commute with each other. dp, dk, dl, I, p, iq of l. For all k, l, p, and q, right? That's what I showed at my previous talk. Now, dk looked like d over dx1n, d over dx2 n minus 1, and so on until we get to d over dxk n minus k plus 1, right? Now the claim is the following. Well, I'm not going to prove it, but it's almost evident. The fact is the following. And it's proved precisely in the way I proved this fact at my previous talk. The fact, if you take I, P, tilde, so hat, L, to be elements in universal and relevant algebra, you take the symmetrization of I, P, L. And you take D hat 1n instead of this, and everything else, right? And that will give you D hat, D capital hat. And the elements in universal and relevant algebra obtained in this way will still commute with each other. So this gives you another commutative subalgebra in universal and relevant algebra, and that gives a kind of quantization of the full symmetric order system. Pretty strange, I'd say. And that's actually easy. It's much easier than. Okay, so let me say a few words about the way this is proved. I'm going to derive this from Tarasov's theorem. So let me recall you, Tarasov's theorem. If you symmetrize iterated derivatives of ik of L and iq of L, and il of k, oh, sorry, il of L, right? Yeah. Then the result that these elements will commute in the universal enveloping algebra. Now, what I'm going to prove, fact which I'm going to prove, is the following. Psi hat P applied to sigma of I K of L is a linear combination of these elements. For the same psi, but with different k's. With k's smaller than that. Sorry, without hat P of I K minus I from 0 to K. No possible. And this, of course, gives you the theorem. So if you just prove that this holds, then well done. And here are the facts that you need to know to prove this. So the first fact, which is interesting by itself because it gives you a kind of an independent point of view on the operators d hat ij, not axiomatic, but say geometric or algebraic, and which gives you an idea how one can extend these operators from GLN to any other Lie algebra. So here is this fact. Consider the operator. Consider the operator theta from UGLN to matrices UGLN and Bayesian matrices, given by the formula theta of F will be equal to identity times F plus the matrix of partial derivatives, well, quasi-derivatives, ij of F. To have a map from UGLN to matrices, you first take the identity matrix multiplied by F, then you take the matrix of quasi-derivatives of F and consider the sum. Then theta is a homomorphism of algebras. And that follows from the Leibniz rule, which we have. The Leibniz rule, and then it had the product of matrices actually over there. And theta is equal to the following composition. If take UGLN, if co-multiply it to UGLN cross UGLN, right? Then you take the standard representation of GLN in matrices. So you just send this abstract universal matrix units EIJ to the concrete matrix units, right? EIJ capital in matrices. So that gives you a map to matrices with coefficients UGLN. Representation on the left, identity on the right. And then theta coincides with this one. So this gives you an idea of how you can actually extend these operators to any Lie algebra. You can even play with representation here. Rho is the standard representation. Rho, yeah, rho of Eij is E capital Ij, the matrix unit, usual matrix unit. Okay. Now we have the following proposition, which follows from this description of theta, and hence the description of d hat Ij, right? If we know the description of theta in terms of in algebraic terms, have description of d hat Ij as well. The proposition is as follows. Consider the map S GLN. First, you take sigma, you end up in UGLN, and then take theta, right? You end up in matrices with coefficients in UGLN. And then you go, well, you decimatize. So to say, you take matrices, sigma minus first, to end up with matrices of Sn. Take this composition. And this is given by the following formula. You take the matrix D and the partial D, the matrix of partial derivatives. The matrix of partial derivatives. You just take exponentially of this D. So you have an infinite differential operator. It's just a form of power series, but when you apply this to any polynomial here, you get just a finite sum. So it's well defined. So you get this method here. And the claim is that it is the same. And the proof is more or less evident if you recall, if you remember that sigma commutes with co-multiplication. Sigma is actually an isomorphism of coalgebras. So here you need to take, so you need to obtain theta, you need to take co-multiplication first. UGLN plus UGLN. So you need to co-multiply here. So there is extended co-multiplication of UGLN as well. Right? Then you take this symmetrization, cancelled, right? Then you take representation. And then you take desymmetrization. So this symmetrization and desymmetrization cancel. They cancel. And you have the following formula. Sigma squared. So that's the lambda square of sigma. The lambda square of sigma. That's the sigma is, and then you have desymmetrization here. And this desymmetrization, it cancels with one of these symmetrizations. It cancels with one of these symmetrizations. And if you use the formula that the co-multiplication in SGLN is given by the exponent of the sum of partial derivatives. I mean, there is a map. Probably better to say like this. You take Dij of f tensor it with the generator Eij. Yeah, Eij, like this. Then you have to exponentiate this map. the sum over the ij's here. So if you take into consideration this definition of commultiplication, so this eij is actually an element in SGLM. And the only thing you need to prove, you will have to observe, is that when you take rho of E I1, J1, I2, J2, E IK, JK, then it is equal to E I1, JK if J1 is equal to I2 and so on, if all these indices match. Either get this or get 0 in no other situations. And that's how you establish this formula, the exponent. Now you need to apply, so instead of psi hat, which is equal to the sum psi ij dij hat, I am going to use the map theta sub psi equal to the trace of the map theta multiplied by the matrix psi. Commutativity of these elements of theta psi p applied to f and theta psi u applied to g is equivalent. Yeah. This commutativity of this element is equivalent to the commutativity of psi hat p and psi hat q, and that's because theta sub psi differs from hat only by the element trace of psi times identity matrix. And for instance, we can assume that the trace of psi is equal to 0. Then this will just be equal to, this is equal to psi hat if trace of this matrix is equal to 0. And we can always assume this. It doesn't change anything. No, so now we need to apply theta sub psi, which is trace of, well, which is just the product of psi and theta, right? To the element sigma of I k of L, right? That's what we need to do. So ik is the coefficient of the characteristic polynomial, right? But theta, so let's forget about sub psi here and speak about just theta first. We'll always get the coefficients back in time in proper places when we need it. So let's consider this. So this theta we apply to sigma of ik, right? So it is equal to matrices, the symmetrization of, when we make it back, of x of d applied to ik of L. Yeah. We just evident diagram search. We get this identity. And if we want to get the coefficients back, we just add these sides here, and that's all. But that's not. Not a big problem. So now we have symmetrization outside. Now we have symmetrization outside. And we know what to do inside, right? And now the following fact. If we take exponent of this partial derivative matrix and apply the determinant of the universal matrix L, and will equal to the sum of I. So this is IN of L, right? The top degree element. IN minus I of L with certain coefficients, universal coefficients, which only depend on this exponent. Sum of I.
N minus I.
Right. N minus I. And that's easy to see. For instance, what is element here? What are elements here? They look like this. I think I probably yeah. Sorry, I forgot to say that we have still the matrix of partial derivatives. Ij d applied to this. So we just replace the exponent by just one matrix by applied to a new combination. That's what I have done. This is the matrix. Right. So here we have IN. Here we have certain coefficients, universal coefficients, which only depend on the exponent, nothing else. And we have the usual matrix here. Just the usual matrix here. And that's it. And then when we want to restore theta xi, we just multiply this by chi here, right? And this, of course, I mean, this symmetrization commutes with multiplying by coefficients. It's just this linear map, right? This symmetrization. So we just multiply it and we just pull psi here, and that's the fact we need. So how to prove this crucial fact? Well, what is the general element in this exponent? It looks like this. It is d I1 I j1 d j. Sorry, let's put like this: k1, k2, k1, k1, k2, k2, k3, d k n j, and we have exactly 1 over n factorial here, right? So that's the generic element in this exponential, in this exponent. Probably better to put m instead of n. N is the degree, is the size of the linear of GLN. So just km. Now the following is true. When we have d a b d b c applied determinant of L, it is equal to d a c d b b applied determinant of L. It's just the property of determinant. If you draw the determinant, then when you differentiate by this, so to say, you erase the bth row and cth column. Then you erase bth column number b, and the row number a. But it is the same thing. You obtain the same thing if you erase this column, bth column number b and the row number b. And then you erase column number c and the row number a. Right? It is this. Now the summation is taken over all case of all possible m tuples of k. So this sum is equal to 1 over m factorial dij sum dk1 k1 dk2 k2 and so on dkm km. But this sum, this operator applied to determinant will give you precisely I n minus m. And the coefficient will be 1 over m factorial, and that's all.
Those numbers.
Yeah. So the lambdas are 1 over m factorial or 1 over m plus 1. It's universal in any case. It doesn't care, it doesn't depend on. So yeah, it doesn't depend on m. So it means that this element will be a combination of Tarasov's element. And then we repeat this property, we repeat this operation, we again obtain a linear combination of Tarasov elements. And that's all. And that's, you obtain linear combination of Tarasov elements because partial derivations, of course, they commute to each other. You can actually change the order of partial derivations and of fuzzy derivations as well. So that's not an easy proof, but still it leads to something. I'm sorry, giving all details is really a little bit boring, I think. But the main ideas, main steps are here. Yeah, that's more or less all. Yeah, sure.
Yeah, thank you very much. Questions, remarks? Anybody left? Anybody left? Okay, then thanks a lot. Gosha, thanks a lot. So we meet in a week, and the next talk will be by Zhenya Feraponto from Library University.